In this section, we're going to be talking about activation energy, which is something that we've talked about a little bit, not much. You might not remember what it is, but this is where we're really going to get into it. And we're also going to talk about the relationship between the temperature of a reaction and its value, the value of its rate constant. So we're going to start with a generalization. In general, not all the time, but generally, usually, when we increase the temperature of a reaction, that causes the rate of the reaction to increase as well. Increasing temperature causes the rate of the reaction to also increase. And we have a pretty simple explanation for this. Our explanation for this is something called collision theory, which I think is pretty logical, and I hope that I can explain it to you in a way that is logical. So collision theory has three basic components or ideas or principles. The first one, something that you learned in 161, as the temperature increases, molecules move faster. So this is something you already know. You should feel pretty comfortable with this. We talk about solids, which are at low temperature. The atoms or the molecules are holding still and they're just kind of vibrating. They're not really moving much. And then for liquids, as the temperature goes up, the molecules move quite a bit faster. And then when we are at a high temperature and the substance is a gas, they're just flying around, moving very quickly. So as temperature increases, molecules move faster. And then if you have a bunch of molecules together, if they're moving faster, they're going to bump into each other more often. As molecules move faster, they collide. We're going to use the word collide. They collide more often. And there's other things that we can say about their collisions as well. I mean, if they're moving really fast, they're going to collide with more force too. But this is really about frequency. If you have a bunch of molecules and they're just, hauling around and flying around and moving very quickly, they're going to be bumping into each other constantly, nonstop. And as they collide more often, when they are colliding more often, it increases the likelihood that two molecules will collide in a good way, in the right way, to lead to a chemical reaction. So if a collision is good, a reaction occurs. In a way, to me, it's kind of a statistics thing. It's molecules bump into each other all the time and they don't actually react with each other. In order for a reaction to occur, the collision has to be just right. It has to be this, what we call good. And so if you want to increase the number of good collisions that occur, you just really need to increase the number of collisions in general that occur. And the bad collisions will increase as well, but that's how we're going to get the good collisions to go up. So let's talk about what it means to be a good collision, because this is also extremely important. What is a good collision? So good collisions have two features. They have two characteristics. Number one, the molecules in a good collision are perfectly lined up. So the molecules line up perfectly. And for some reactions, there's a little bit of help in the alignment due to, let's say, charge differences, like the negative end of one molecule being attracted to the positive end of another molecule. And sometimes those forces kind of help with the collisions, but not a lot. A lot of it is just random. So at the instant that they happen to bump into each other, they're perfectly lined up with each other. And I'm going to draw a picture of this example of a perfect alignment. The other thing that needs to happen in order for a collision to be good, the molecules have to hit each other pretty hard. Molecules must collide and bring into that collision enough energy to break any kind of bonds that need to be broken. And breaking bonds takes a lot of energy. So they have to collide just right, and they also have to collide with a lot of force so they can just slam those bonds apart. So what does this good collision concept look like? Well, let's take a look at an example of a reaction that we study very early in organic chemistry. And I'm going to draw this molecule three-dimensionally. This is a carbon with a bromine and 3 hydrogens on it. And so in one of the things that will react with this particular molecule is a hydroxide ion, which I'm actually going to draw backwards from how you're used to seeing it. And the reason for that will become clear in a minute. And so in this particular reaction between these two substances, the oxygen of the hydroxide ion has to bump into the carbon atom. It can't collide anywhere else. It can't bump into the hydrogen. It can't bump into this hydrogen. It can't bump into the bromine. Those are all wrong. It has to hit the carbon, and it also has to hit the carbon exactly opposite of the bromine. So like if you can imagine carbon as a sphere with the bromine hanging off of the carbon, the oxygen has to hit the carbon on the total opposite side of the bromine. I feel like my drawing probably isn't really conducive to showing that. I'm going to modify my drawing a little bit. I'm going to put the bromine up here because I think it's easier to show the oxygen lining up just right. So the oxygen has to come in and hit the carbon from this angle. It could not collide from this angle or from a different angle. Those collisions would be not lined up correctly. So the alignment is very important. And when it lines itself up perfectly, then if it has brought enough force with it to break that carbon-bromine bond, a reaction will actually occur. So if you think about it, it's kind of a miracle that any reactions take place at all, because things have to really be perfect for any kind of chemistry to take place.